Image reconstruction is the process of turning raw data collected by the detectors into image data which can be viewed on a screen. Both raw data and image data can be manipulated in different ways to create images with differing properties. The most rudimentary process of turning raw data into image data is called back projection. This is the process of mathematically mapping the attenuation pathway at every angle measured through a scan to locate where in a patient attenuation is occurring. If there is a dense object at this location in a patient, then a projection at this angle will show us attenuation in this area because less photons will be arriving at the detector through this attenuation pathway. When we apply that same principle from various angles through the patient, we can map where that dense object is within the patient and generate a cross-sectional image that shows the object. The star pattern you see here is a natural drawback of the back projection method, but it's reduced to an extent by the fact that we have many other angles showing where there is or isn't attenuation. The beam in this direction, for example, tells us that there is no dense object here. This means that the more projection angles we have in our data set, the greater our image quality will be. The relatively simple process known as back projection is now applied within another process called filtered back projection. All that this means is that a filter is applied to all of the data that's put through the back projection process. A filter, also referred to as a kernel or sometimes just as an algorithm, is a form of data pre-processing, and it's an algorithmic manipulation which alters the value of a pixel and its neighboring pixels relative to one another. So, for example, if we want to see very sharp edges and details, we would apply a sharpening filter, also known as an edge enhancement or high pass filter. And what that does is it drives the value of each pixel away from the value of its neighboring pixels. So in this example, we have an interface between a dark gray and a light gray pixel, and we're going to apply a sharpening filter. And when that filter is applied to this middle pixel, it's going to take its neighbors and drive their values away from the average value of these three. So the dark pixel becomes darker and the light pixel becomes lighter. Conversely, if we use a smooth filter, also known as a blurring or a low pass filter, we're going to do the opposite and make this sharp black-white interface into a much smoother gray to gray transition. So we're averaging this pixel out with the value of its neighbors. With filtered back projection, we're applying these mathematical transformations to our whole data set when reconstructing it. So every pixel is individually going through some kind of algorithmic manipulation relative to its neighbors to either give us a sharper or a smoother set of images. This has a direct impact on the properties of our image because a sharpening algorithm is going to give us higher spatial resolution and crisp, sharp edges, but it's also going to make the noise more prominent. Whereas a smoother algorithm is going to blur and smooth out that noise, but at the cost of also blurring out our nice sharp edges. So, as with everything in CT, there is this trade-off between whether we want to see sharp or smooth images. And in some scans, you're going to reconstruct both sharp and smooth sets of data, which can each be used to view different structures within one scan. For example, with a chest CT, you're going to reconstruct both lung and soft tissue data sets from your raw data. The lung images will be reconstructed with a sharp filter, so we can see small nodules and fine details in the lung tissue with high spatial resolution. And the soft tissue images will be reconstructed with a smooth filter, so we can look at the structures of the heart and the mediastinum with reduced noise and therefore with better contrast resolution. In a previous video we discussed windowing, and each of these different data sets are also going to have different windows applied as well, because we're looking at different structures. So two different filters are used and two different windows are used to view these two different reconstructions from one raw data set. Beyond filtered back projection, another method of reconstructing raw data into image data is called iterative reconstruction. Iterative reconstruction is a repetitive process which starts with a filtered back projection, which is treated as an estimate of the true data set, and then each data point in this estimate is compared to the scan data to see how close to the true value it is. This process happens in a cycle repeatedly until a certain predetermined number of iterations has happened, and at that point the assumed image has then been repeatedly refined and is going to be very close to a true representation of the data. The advantage of iterative reconstruction is that both noise and certain artifacts in the image can be reduced, because both of these things are non-true representations of what should be in the dataset. So with every iteration we're reducing these inconsistencies in our data. The increasing proliferation and effectiveness of iterative reconstruction algorithms has meant that we are able to reduce the radiation doses used in CT scanning, because any form of noise reducing technology means we can settle for more noise in our data and then reduce that noise with the power of computing. So a lot of the dose reduction strategies which various vendors have developed recently in CT have been driven by improvements in iterative reconstruction software, alongside a growth in computing power that has enabled these complex algorithms to run much more quickly. After reconstructing our image data from the raw data, we can apply several other manipulations to those images. Multiplanar reformats, or MPRs, are reconstructed in almost every CT scan performed today, and what this means is simply putting our data together to view it from a different orientation. Because a set of axial images is basically a lined up row of voxels displayed as pixels, we can effectively stack all those slices on top of each other and view the voxels from any angle. So we can manipulate those axial images to be viewed in the coronal plane or the sagittal plane or even an oblique plane through the body. In most scan protocols, the scanner will have preloaded instructions to generate an axial image series from the raw data, and then to generate MPRs in the coronal and sagittal planes from that axial data. If thick axial slices are used to reconstruct the MPRs, the coronal and sagittal images will have a jagged appearance known as a stair-step artifact at the interfaces of each of those slices. So routine practice is to reconstruct an axial dataset in the thinnest possible slices from the raw data with overlap, and then to use that thin dataset solely for the purpose of generating MPRs. When generating reconstructions in any plane from a thin set of image data, there are a few ways to render these slices. If, for example, we're using a set of 0.5mm slices to generate a 3mm slice, the simplest and most common way to render that 3mm slice would be to take all those stacked 0.5mm voxels and to average them to give us a value for the voxel represented by that 3mm slice. This is how normal images are made, and it's referred to as volume averaging because you're averaging all the values within that volume. This isn't the only way to render that data, however. We could also take the maximum value represented within that 3mm volume and take that maximum value to represent the whole voxel. This is called a maximum intensity projection, or a MIP. Similarly, we could take the minimum value represented within this volume and take that to represent the whole voxel. This is called a minimum intensity projection, or a min-IP. While volume averaging is the most common mode of rendering image reconstructions, MIPs, and to a lesser extent min-IPs, do have certain applications in which they can be useful. For example, if you're looking for tiny lung nodules, a MIP may be used to bring out and highlight nodules which are smaller than your 2mm slice, for example. On the other hand, if you want to only look at the airspace in the lung, a minimum intensity projection will give you a very black image to see airspaces without obstruction from lung tissue which might otherwise occupy the same voxel. The last manipulation to discuss is 3D reconstructions. Because a set of thinly stacked axial images is comprised of volumetric information, we can use that volumetric information to generate a 3D image that represents the volume. Surface rendering techniques can be used to detect a continuous surface within a volume of data. Volume rendering techniques can be used to render the full scope of 3D data and see various tissues in conjunction with one another. As always, thanks for watching and keep up the hard work.